Chemsters, this is Mrs. Vanderlei bringing you Blankwalle, Chapter 12, Section 6, Part 2, all right? So what we just accomplished in Part 1 is we talked about different properties, well, colligative properties, and we really only focused on the vapor pressure. And what happens is that if you put a polar or ionic substance into solution, it will affect the amount of molecules that will enter the vapor phase, okay? Why is that? If you recall, only polar or ionic things can dissolve because they are the only ones that have the attractions to dissolve in the water. And if there are attractions in the water, that's going to keep the water molecules from entering the gas phase, lowering the vapor pressure. Well, that was all under the assumption that the solute was non-volatile. And what does that mean? It does not evaporate. So what happens then if I do put something in that will also evaporate? Okay, what about rubbing alcohol in water? Rubbing alcohol evaporates and water evaporates. So what happens if I were to mix the two? Well, let me think about this. So let's call the red dots, all right, this is my water, all right, these are my water molecules, all right, and what's going to happen with my water molecules? All right, some of them near the surface are going to do what? Evaporate, okay? And then if I add some green rubbing alcohol, here's my green, I added the solute in here, and what can happen to my green rubbing alcohol? Oops, take that back. Okay, some of my green alcohol can do what? Can also evaporate, all right? And so what's going to determine the amount of alcohol and the amount of water that's going to evaporate is how much are they attracted to one another. So the amount of red dots that I have here will depend on the attraction the green has on the red. And the amount of green dots I have here will depend on the attraction the red has for the green. So this mutual attraction is going to affect the amount of vapor in both the green and the red, or the water and the rubbing alcohol. And so how do I figure out the total solution? Well, I'm going to add the red and the green. I'm going to add the vapor pressure from the water with the vapor pressure of the alcohol. So this is what's called a modified Raoult's law, all right? And again, if you look on your equation sheet, you're going to see this again, okay? And really, all what this is Dalton's law of partial pressure. All right, so make a note of that. This is just Dalton's law of partial pressure, which is also on the equation sheet. And again, I'm defining the P naught is the vapor pressure, the pure solvent, pure A or pure B. And the P with a little a and the P with a little b are the partial pressures that are resultant from this solution, okay? Well, now we have something called an ideal solution, liquid-liquid solution that obeys Raoult's law perfectly, okay, where they have, you know, the predicted attractions, they have the predicted vapor pressure that the math would give us, all right? The problem is no solution will exactly follow the modified Raoult's law, although some will be kind of close, okay? So we have two kinds of deviations, all right? We have negative deviations from Raoult's law and positive. And I know I can't, well, I guess I can. Let me scroll down. Whoops. Well, that didn't work out. Hang on. So here's my negative deviations from Raoult's law, all right, right here. Well, let's kind of look at this graph first. Let me scroll down just a little bit so I can see the whole graph. First of all, what is this? This is ideal. So if I were to do the math of that modified Raoult's law above, I would get a graph like this. So why is it crisscross? Well, this would be like maybe part B. Maybe this is your solute or your solvent. Don't know which, okay? But if I have a pure, let's make it, I don't know, solute, then if I had pure solute, then the vapor pressure would be that of pure solute. If this were my, let's go this way, if this were my other one, my solvent, okay, then this would be the vapor pressure of the other one, okay? So notice that this right here is your mole fraction of A. All right, so if I have pure A, that's what this line is right here, then I'll have the vapor pressure of that pure A, okay? And as I add more and more in B, my mole fraction goes down, well, so is the vapor pressure of A. Well, this is my pure B. Notice what is going on here. If I have a 1 pure A, that means I don't have any B. And this is telling me I'm adding B, so the mole fraction of B goes up and the mole fraction of A goes down. But what will these two always add up to? 1. Just keep that in mind, okay? They'll always add up to 1. And so when you do that, you're adding the vapor pressure both, and that's what this line represents. This is your math, okay? This is what it should be. But like we said before, ideal, there is no such thing as an ideal solution. And we have something called negative deviations and positive deviation. So this right here is your negative deviation. That means that the vapor pressure is actually lower than what it should be. And why would I have lower vapor pressure? It means I have lower vapor molecules. Why would I have fewer molecules in the vapor phase? It's because there's too much attraction or a lot of attraction in the liquid phase. So it's going to take more and more energy to break free. And if it takes more energy to break free, the heat of solution is large and negative, all right? So it's going to release energy when it breaks free. Okay, they have strong forces of attraction. All right, so positive deviations, that's when you get more than the predicted vapor pressure. All right, why would your vapor pressure be actually more than what your math, that's what this dotted line is, this is what your math is telling you it should be. Well, you have more gas or more vapor molecules than I predicted. Well, why would you have more gas molecules in the gas phase than you thought? Well, there apparently were a lot of attractions going on in the liquid phase, so more of them can easily break free. All right, so they have only weak forces of attraction. I highlighted that, and particles can escape easily and enter the vapor phase. Okay, so let's go back real quick. I don't know if I really made this clear to you. The heat of solution is large and negative. What does that mean? That means when you dissolve one into the other, it's going to be exothermic. Okay, that's what that means. Okay, let's go to the problems. Let's go to the next page. All right, so a solution is made by preparing 5.81 grams of acetone, which is C3H6O, and 11.9 grams of chloroform, which is 119.5, and there's its formula. At 35 degrees, the solution has a total vapor pressure of 260 torr. Is this an ideal solution? So what I need to do is I need to actually calculate the vapor pressure using the modified Raoult's law and then compare it to that 260 torr. I will not actually use the 260 torr in my work. I'll compare my work to that number. And then it says the vapor pressures of pure acetone and pure chloroform are 345 and 293 torr respectively. So I, first of all, gave you the molar mass of each, so you don't have to get out your periodic table. I gave it to you. And then I just said, okay, let acetone be A. Well, duh, it starts with A. And chloroform be B. All right. So I first need to find the partial pressure of acetone. Well, in order to do so, I need to know what chi is, don't I? Well, what is chi? It's the mole fraction of acetone over acetone plus chloroform. Well, I need to know the molar masses. I'm sorry, I need to know the moles. I got the molar mass. Folks, look, here's my grams, here's my molar mass. Wow, isn't that easy? What's 5.81 divided by 58.1? Isn't it 0.1? And then what? Oh my gosh, I made this so easy. What is 11.9 grams of chloroform divided by 119.5? That's really close to 0.1, all right? Ends up being, if you do your math, 0.0996, okay? So using, a little bit of mental math here, well, what do you think chi is really, really, really close to? Well, it's pretty close to a half, isn't it? Isn't this almost 0.2? It is. So there is my chi if you do the math. If you're following along with your calculator, hopefully you get the same thing. So now I can find out the partial pressure of the acetone. All right, so the pressure is equal to pure plus, or times the mole fraction, and I get 173 torr. Well, guess what? I got to do the same thing now with chloroform. All right, so my chi is moles of chloroform over this whole thing. But let's save ourselves a little bit of work here, okay? Hey, what do the two mole fractions always add up to? 1. So if this chi is 0.501, guess what this one is? 0.499. Ooh, that makes it easy, doesn't it? So now I can just do this, and I know what my pressure of B is. Well, am I done yet? The answer is no. Let me scroll down a little bit. That's not what they asked for. What are the partial pressure of acetone? What's the partial pressure of chloroform? But I do need to know those in order to do this, right? So what is the total pressure of, well, it's equal to PA, or the acetone, plus the partial pressure of the chloroform. So I'm going to add these two together. And when I get done, I get 319, which is what? That's what I should get. If this were an ideal, that's what I should get. But wait a minute, what did I actually get? I got 260 torr, and that's less than 319 torr. That's what I got up above. So why do I have fewer molecules in solution than I should get? That means they must really like each other, so the liquids don't go into the gas phase, all right? So it is called a negative deviation. Why? Because this is less than what I should have. And why do I have it? I must have some pretty strong attractions, okay? So why don't you do problem number 18 by yourself? And I mean it. So pause this. It's probably going to take you a few minutes to do all the calculations. Please don't watch me do it. You need to do this, all right? And then when you're done, come back and see how you did. All right, so this is what I did. Well, I first need to know what my chi is, and I'm going to let my carbon disulfide be my A. I should probably make it my acetone, but I'm sorry. It's the first one listed, so I'm going to make carbon disulfide be my A, and I'm going to let acetone be B. All right. Well, I'm sure you could have done this yourself. This is the math I got. This is my moles of carbon disulfide over my moles of carbon disulfide plus moles of acetone. And so when I got that all together, it looks like I got 0.544. Hang on, where'd it go? Don't see you. Okay, I found it. So then what? I need to know what my partial pressure of A is. So I'm going to multiply that 0.544 times the pure stuff, which is 515. And when I do that, I got 285. There you go, 285 torr. Okay. Well, I'm going to do the same thing, all right, over here, whoopsie, of B. I guess I'll do that. And so here's my mole fraction. But wait a minute, do I actually have to calculate all that? Of course not. What do I know about my mole fraction? These two have to do what? Add up to, wait a minute, that doesn't add up though, does it? Oh, this is 554. I didn't fix it. There we go. 0.446. And then what happens here, I'm going to do this and then get to that. But I'm not done yet, am I? What do I need to do? I need to find the total pressure. Well, I'm going to do this. And then I'm going to add them together. And I'm going to do this. And I get, what, 433 is what it looks like. There we go. There we go. That's what I should get. But wait a minute, that's not what I did get. I got 645. That's what it says up here. I got 645 torr, which is what? Greater than 433. It's a positive deviation. So why would it have a positive deviation? Well, there must be weaker than expected attractions, okay? Whoopsies. And so this is how you do the Raoult's law. So let's scroll down, and the question is, what factors do you think are going to affect the boiling points? Hey, that's a really good question. Well, hopefully by now you figured out, well, what kind of solute and solvents you're going to have. Why would I guess that? Well, duh, that's what we've been talking about with vapor pressure. Isn't vapor pressure associated with boiling points? Oh yeah, when the vapor pressure of your stuff is equal to the outside pressure, that's when it boils. So what affects vapor pressure is probably going to affect boiling points. Hey, and you're right. And then not just what solute and solvents you pick, but isn't how much you have part of it? And the answer is, well, yes. Why? Because that mole fraction is kind of involved in that too, all right? So this is a really good place to pause. And so, of course, I'll say don't wait to be great. We'll see you shortly in part 3. Bye-bye.